In this video, we're going to take everything we've learned about derivatives and how they relate to functions in graphs in order to try to use that to draw a more accurate graph of a function. Before we get started here, I will make my own personal comments that this is a very standard section in Calculus 1 courses, and it is important for you to understand all these different things here and how they relate to functions. But the actual process of manually drawing the graph, I don't consider that important these days. With current technology, graphing calculators, computer software, websites, and so on, I consider that to be a much better way to get an accurate version of a graph than trying to do it by hand, even if you know all of these techniques here. So that's just my personal preference. Regardless, as I said, it's still important to understand how these things relate, and we are going to cover it. But the actual drawing of the graph is not that big of a deal in my opinion. So I have a checklist here of all these different things we're going to want to look at when trying to draw a graph. The nice thing is that you can pretty much do them whatever order you want to. So just kind of your personal preference, what seems like a good way to start. With that said, I'm going to just do them in the order I have for now. So we look at domain here. And in your algebra classes, you should have went over a whole bunch of different rules for domain and how you find it. And the thing is that it's pretty difficult to try to talk about all of them right now because there's just so much out there, and I'm not going to try to do that. But just remember that there are lots of rules depending on what type of function you have, and you're going to want to look at those rules up again if you've forgotten some of them. It's an easy thing to do. So for this case, we have a fraction here, and we know that when you have a fraction and you're trying to find the domain, then you're going to go ahead and take the bottom and set it equal to 0. And that's all you need to do for that. So we take the bottom, set it equal to 0. And we're going to get two values of x. And the thing is, these are the values of x that would make the denominator 0, which means these are the values of x that will simply not give us a valid answer here. So our domain is everything except for these numbers. Okay, so there's our domain. Next we have x and y intercepts. I'll go ahead and do x-intercept first. That's when your function is equal to 0. And so in this case, I set this thing equal to 0 here. And I want to point out something. When I go ahead and multiply to clear out the fractions, you'll notice that on the right side, I get 0 times anything is still 0. So it turns out for these, we don't even really care about the bottom. We just look at where the top is 0. And that gives us our x-intercepts. Now the next thing that we need here is we need y-intercepts. And y-intercept is when you plug in 0 for x. So in this case, 0 plus 2 over 0 minus 9. So we're going to get the point negative 2/9 on y. So let me go ahead and mark these here. My x-intercept is at negative 2, 0. My y-intercept is somewhere negative 2/9 on the y-axis. Obviously, I can't be sure that that's really negative 2/9, but I'm just marking a point right there. I do know it's negative, so I do know it's at least a little bit below the x-axis, but exactly how much is hard to say on a graph like this. So we got the x-intercepts and y-intercepts in the domain. Then we look for asymptotes. There are two types of asymptotes. One is vertical asymptotes, and when you have a fraction, the vertical asymptote happens by taking the bottom, setting equal to 0. We actually already did this. And so these are going to be our vertical asymptotes. Notice, though, that it's not equals this time. X equal to 3 is a vertical line, and x equal to negative 3 is another vertical line. So that's the correct way to write down your vertical asymptotes. Next thing we need are horizontal asymptotes. And you learned in your algebra class that there are certain tricks to get the horizontal asymptote. In this class, you're going to take a limit of the function as you go to infinity and negative infinity. Now for this one, it's just going to be 0 for both directions. But obviously if you have a more complicated function, like for example one of the ones with the square root, it might be a real pain here. So that's our horizontal asymptote. Now personally when I do these, I always draw horizontal asymptotes in green and vertical asymptotes in red, because a vertical asymptote you cannot actually cross, period. It's a red dotted line for stop. You do not cross that line. However, horizontal asymptotes, it is possible to cross that line, and then that's why I put green there. You can pass it. Got our asymptotes there. Then we need to do some derivative stuff here. So let's take the derivative of this function. We're going to need the quotient rule. Derivative of the top times the bottom minus the top times the derivative of the bottom all over the bottom squared. And if we simplify some things on top here, I'm going to have a negative x squared minus 4x minus 9. And we're going to want to know where this thing is 0 to find our critical points. Well, as we said a little while ago, the denominator is not going to affect when it equals 0, so we just use our numerator here. And we can use our quadratic formula, negative b plus or minus b squared minus 4ac all over 2a. Sorry, well 2a, but in this case it's negative 2. And then we notice here that inside that square root is going to be a negative number. So we're going to have imaginary number answers here. And if you get imaginary number, that means that there are going to be no critical points. It's never going to be 0. Now what that means is if you're looking for when the derivative is positive or negative, there's no critical points to mark. However, there are points to mark because of your domain here. There's a break in the function at 3 and another break at negative 3. So then we just need to look at positive and negative in this region here. So if I look at 0 on the derivative, I would get a negative answer. If I were to look at, let's say, 5, I'm going to get a negative answer. And if I look at this, it's going to be negative. So that means this function is decreasing everywhere. But I should say that it's decreasing specifically negative infinity, negative 3, then negative 3, 3, then 3 to infinity. Now since it never changes between increasing and decreasing, that means that there's going to be no local min or max on this graph. And then the last thing we need to do is concave up and down, so we take our derivative here, second derivative, and it's a bit more of a pain here, so derivative of the top times the bottom, running out of room here, minus the top times the derivative of the bottom all over the bottom squared. And then there's going to be some fun algebra here. Turns out everything has an x squared minus 9 in common, so I can cancel 1x squared minus 9. Minus 2x minus 4, 1x squared minus 9, minus negative x squared minus 4x minus 9 times 4x over x squared minus 9 cubed. And then we've got to do our best here. Let's see, I'm going to have negative 2x cubed and a positive 4x cubed. It's going to become a 2x cubed here. And then I'm going to have, let's see here, for x squared terms, I would have a negative 4x squared and a positive 16x squared, so positive 12x squared. And then for x terms, I'd have an 18x plus 36. 18 and 36 is 54x. and then plus 36 all over x squared minus 9 cubed. And again, you would try to make yourself a sign chart here. We certainly need to mark 3 and negative 3. And then we need to see if that top part's ever 0. It's a bit of a pain here. Now again, when you're given these, you just gotta do your best, as much information as you can get out of this. In this particular case, I'm actually going to use a calculator to help me look at that top part there. So we'd have 2x cubed plus 12x squared plus 54x plus 36. And if you were to look at a graph of that, you are going to cross the x-axis in one place here, and using our calculator to get an approximate value of that, we get an approximate value of negative 0.785. Now, anyone I actually give you on a test or so on, you just go ahead and it'll work out a lot nicer than this. This is just an example here. So we got to figure out positives and negatives here. On this case, we are certainly going to have positives for big values over here. Then when you get down below 3, say you plug in 0, you're going to get a negative answer. Then when you go ahead and plug in, say, negative 1, you are going to get a positive answer. And then lastly, you're going to get a negative answer over here. So we see where it's concave up and concave down and so on. And so the last thing we want to do is fill in our graph. Well, we know we're going to connect these here. And we know that it can't cross the x-axis anymore, so this one's going to have to go down towards the vertical asymptote, and this one's going to have to go up towards the vertical asymptote. And then if I use multiplicities here, the multiplicity of the vertical asymptotes is only 1, which is an odd number, which means if it goes down on one side, it's going to go up on the other side and go towards 0. And similarly, if it went up on one side, it's going to go down on the other side. And so you can kind of see here, it starts out concave down, definitely decreasing. It starts out concave up in this part, and then switches to concave down, still always decreasing. And the third one here, it's always concave up, but still decreasing. I do want to point out something important right here. I see students make this mistake a lot. When they get decreasing, and they see all of these are minus, 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 they will then say that it is decreasing on negative infinity to infinity. But if you do that, that is actually wrong. It's not just a different way of writing it, it's actually wrong. Because if you say decreasing from negative infinity to infinity, that means your graph is always going down every time you go from left to right. But if you look at your actual graph here, you're going down, and then you jump. So you went up for a little half a second there. And then you're going down, 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 and then you jump for half a second, and then down, down, down. So if you wrote decreasing from negative infinity to positive infinity, it would actually be the wrong answer. You do need to write it out separately here because the graph is 3 separate places where they're all decreasing. And it's important for you to understand the difference there. Now the one thing I didn't really talk about here is symmetry. That's again something like if you have symmetry around the x-axis or y-axis or so on, it can help you draw graphs. It's something you really want to have, your last step is you want to just think about if you have it or not. Most random functions that I put in there are not going to have nice symmetry, but some of them would. And it's just something good idea to keep in mind that it might be there. And so this is how we take all of our information and draw a graph.